I'm on messy TikTok.
Although they often strive for perfection, they can feel lost in their own chaos.
Hello, everybody. Yes, you can hear me.
Hello.
Thank you. Yeah, that helps. Zoom in so that I can make some. Homework 2 is due Monday.
The Xbox One S and then the controllers. Do all of those controllers over there work for the Xbox One, or are you sure?
Let me mute everyone. Okay. I don't see the bigger chart that I have, so if you're not able to see very clearly, let me know. I can probably zoom in a little bit more, but do let me know if it's bothering. I should mention that solutions has been posted for homework 2. Usually I post it a couple of days before, but I happened to have time yesterday, so I made the solutions. So solutions posted, and midterm 1 is 2 weeks from Monday. And hopefully by now you have a feel for the routine of the course: quiz every lecture, homework about every week. It's not going to be always Monday, but about every week, and every 4 weeks we have a midterm. So that's going to be the pattern. Any comments or questions you would like to point out? Anything about the course? Okay, so let's get to, we were talking about motion in 1 dimensions, and since we already have the equations now, we collected all the equations. There was a small comment made last lecture that are you expected to derive all the equations? No, the way it was derived in the class, that's very general. So probably not in that form, but each of those steps are relevant in a particular problem. So yes and no, the answer to that question is yes and no. it won't be necessary to derive at a very general level, which is very abstract and require more understanding of the system. But for a specific problem, when the numbers are given to you, you should be able to manipulate the equations algebraically, at least if not using calculus, to get the required answer. And now that we have the equations, I will call it the kinematic equations of motion in one dimensions instead of motion in one dimension. It's the same idea, but we call it kinematic. So it's a kinematic has to do with motion, and later on we will ask what is the cause for the motion. That will be Newton's law. That will be called dynamics. So dynamics and kinematics are different concepts. So kinematics is we don't ask about what is causing the motion. For some reason, there is a motion with uniform velocity or uniform acceleration or a generic acceleration. So kinematic equations of motion. And there are two particular types we are interested in. We, to begin with, using calculus, did it for any general motion. Given the acceleration, we can get the velocity and the position by integration, or given the position, we can get the velocity and the acceleration by differentiation. But two very particular cases are of interest because it becomes algebraic. We don't have to worry about instantaneous velocities anymore. It's just the initial and final points are sufficient, and that makes working on the problems very easy. So let's particularly talk about uniform acceleration. That's what we did last time. And uniform velocity is part of this itself. You just have to set acceleration equal to 0. We said there are 5 variables involved in this scenario. And the equations were delta x over delta t equal to v final plus v initial over 2. Second was v final is equal to v initial plus a times delta t. Then that is displacement is equal to v initial delta t plus half acceleration times delta t squared. One more equation very similar, but this is in terms of v final. That is a difference between the two. One is in initial velocity and one is the final velocity, and that is a subtraction of the acceleration term. And finally, you have 2 times a times delta x is equal to v final square minus v initial square. Out of these 5 equations, only 2 are relevant. If you are really reasonably comfortable with algebra, you need any 2 of these equations. Most general out of this is the second and third. This is what you will see in most of the textbooks. That is sufficient. And in fact, any 2 equations is sufficient, but rest of them are not independent. They can be derived from any of the other 2 equations. So if you're good with algebra, you can take any of these 2 and work on every problem the way you want to. But often, if you're not comfortable with algebra, you don't want to manipulate equation in every problem that you're dealing with, then I suggested a strategy that you look for a missing variable. So each one of these equations has 1 variable missing. So the first one has acceleration missing, second one has displacement missing, third one has the final velocity missing, fourth one has the initial velocity missing, and the last one has the change in time missing. And those are the 5 variables. So in general, a problem in kinematics will involve 5 variables. Out of this, there are only 2 independent equations. So there can be only 2 unknowns. So 3 variables have to be given. And that's usually the way to look for in a problem. Look for 3 quantities in there. So let's do an example where we clarify the use of this equation. And let's say I move the this example also shows up in your homework, at least in 2 different problems. So let's say, or before that, I should mention that, actually I should point out. So let me move the board a little. So before I proceed and do a specific problem, there is one set of problems where there is an implicit understanding, and that's called free fall. By free fall, we mean we know that whatever we drop on the surface of Earth, it goes down, it tries to reach the center of the Earth, but there is a surface of Earth that stops it. So at least until it reaches the surface of Earth, it keeps falling. And the question is, at what rate does it fall? So if you were to drop a stone or a ball, it starts from initial velocity 0 and it gains velocity, right? In 1 second, it gains some velocity, right? So V final, let's say, is not equal to 0. So it gains some velocity, and in the next second, it will gain some more velocity, and it turns out that it gains velocity linearly. The velocity it gains is linear, but the amount of distance it travels is quadratic. So the amount of distance it will go, if this was 4 meters, and in the next second, it would have gone 9 meters. So this would have gone much farther. So that would have gone 9 meters there. In the next, by 3 seconds, you would, or in the first 2 seconds, this will be 4. This is 3 square, that's 9. In the next second, it would have reached 16. So it is growing very quickly when it comes to distances. So x initial, it could be 0, and x final is given by 4, 9, 16, and so on. We'll see that as we go. But the point is, what I'm trying to say is that when we say free fall, this rate at which it is increasing is very specific. Like that's decided by the acceleration due to gravity. So, of course, this stone is accelerating. So you ask, what is the acceleration? So that's a special acceleration. So it's called acceleration due to gravity. So it's falling under the gravitational force of Earth. We will talk about what gravitational force is. I haven't really specified at this point. What we need to know is that it causes this stone to accelerate. Later we will come and later down the semester, we will make it more precise and say why exactly where do we get this 9.8 meters per second square acid. So what is the acceleration? This will be equal to minus g. So let's say this is a vector. This is going downward, right? So let me say this is 9.8 meters per second square. If it's a vector, then I will write a unit vector and specify this. So 9.8 meters per second square downwards. So if velocity is also going downward, that means it is accelerating, that is increasing its velocity. If by any chance, if you were to throw a stone upward, then velocity is upward and acceleration is downward, that means it is slowing down. If they are in the same direction, that means it is accelerating, that means it is increasing its velocity. If they are in opposite direction, that is slowing down. And it seems like it is a mysterious number, right? Why 9.8 is, of course, it depends on which units you're using, but even otherwise, why 9.8? Where does it come from? What decides that's 9.8? That's a good question, and we will address this as we go down in the semester. For example, if you were to drop a stone on another planet, let's say on Mars, will it actually fall at this rate? Will it be 9.8 meters per second square? No, it will not be. But then what will that number be, and what decides that feature? We will come to that later on. So for now, whenever we are on the surface of Earth and whenever we are dropping something, it's understood that this is acceleration is downwards and it is 9.8 meters per second square. We will in fact use a letter, special letter for this all the time, and this will be, whenever you use G, this will be plus 9.8. That's the magnitude of this acceleration. Right? So that's standard to have small g. Later on, we will also use capital G. That's a different variable altogether. But here, this will be a constant. So G is the acceleration due to gravity on the surface of Earth. Is there a third digit in there? Yes, there is a third digit in there. And it changes based on where you are. So if you are, because Earth is not a perfect sphere, for example, if you climb a 5 kilometer high mountain, then this might get weaker. Or if you go into a valley, which is a kilometer or two deeper, then this might get weaker. So in general, this varies between 9.75 to 9.85. But then instead of specifying where you are, it's easier to keep it to 2 significant digits. So we will work all our problems with 9.8 meters per second square, which means it's 2 significant digits. Your answer should have only 2 significant digits at the end, because this will contribute to the error in the problem. Okay, so with that information that acceleration due to gravity is 9.8, let's work on an example where we actually drop something on the surface of Earth. So let's say you're on a building. So this represents a building, and that's a ground. It's a flat. In principle, this is the surface of Earth. It actually curves down there. But currently, when you're so close to Earth, if you're within 10 kilometers or so, Earth is pretty much flat in that approximation. So that's why we don't perceive any, or you have to do some very good experiments to be able to realize that Earth actually is curved. But naively, it looks flat. So that's a building, and let's say one of us is standing on the roof of the building, and let's not worry about the height or wherever you're throwing from, that will be our height. So let's say this is your height, and let's say this is about 20 meters. So it's a 3-story building. So 1 story is typically 6 meters. So it's about 20 meters. So 2 significant. So I put a decimal there, so that means it is 20 meters. I throw a stone up in the air, so it goes up and then it comes down. And whenever we talk about these motions as an initial and final point, it is often a confusion that, oh, what are the final velocity is going to be 0 because it lands on the ground and eventually comes to rest, right? Once it hits the ground, eventually it will come to rest. But that's not the point. These equations, kinematic equations of motion, when it's accelerating, it is right before it hits the ground, an instant, a tiny instant before it hits the ground. So we are not talking about the question of after it hits the ground, because our equations do not work beyond that, because it's not accelerating beyond that. So that's our final point, if you want. And this could be our initial point. And I have to still frame the question. So that's our 20 meters. And let's say you throw this with some velocity. So it's typically easy to throw at 5 meters per second. So let's say V initial is equal to 5 meters per second. So this actually, at the moment I say 5 meters per second, I should clarify, we typically don't work in meters, right? We are used to driving on interstates, we are used to miles. So we should have a reasonable, at least an intuitive connection between meters per second and miles per hour. So that's good to have. It's not like, of course, one can always convert 1 mile to one kilometer. So 1 mile is approximately 1.6 kilometers. So if you are given, someone is going at 70 miles per hour, if you have to convert it into kilometers per second, of course, you can replace 1 hour with 60 minutes, 1 minute with 60 seconds, and 1 mile with 1.6 kilometers. Yes, that's good. But often that detail actually takes away some intuition, and you would like something to be immediately, right, while you're driving without any pen and paper and hand, you want to have an intuitive feel for what is going on. So here is a point. So suppose you're going at 70 miles per hour, right? That's equivalent to one significant digit. There's a huge error in whatever I'm writing, but with that much error, we are talking about, when I say one significant digit, that means 10% error. So that's what, if you're ready to survive with that, this is approximately, just divide by 2, right? Approximately one significant digit. So this is 2 significant digits, right? So that's not accurate. So this is meters per second. So why do I say it is one significant digit? So this is either 30 or 40, right? It could be between 30 or 40. What is it exactly equal to? So this is supposed to be 31.3 meters per second if you were to do it correctly. I think somewhere around that. Let me say 32 meters per second. If you keep the second digit also, I think it is 32 meters per second. But if you want to do that calculation, and if you're driving and you want to have some intuition of based on your experience in the classroom, that might take away some effort there. So it's good to just divide by 2. So any number in miles per hour to a 10% accuracy is just divided by 2. So that gives you an idea. Oh, yeah, I'm traveling at 40 miles per hour on the main street in our city. That means it's 20 meters per second. So that's a good thing to have. So 5 meters per second is about 10 miles per hour. So that's the speed at which you're throwing the ball up in the air. It gives a feel for, because we are used to the driving speed so much, it's good to have an intuitive feel there. With that information, so I have one information here, second information here, and remember the third information is implicit in the sense that this is falling under gravity, so it is acceleration due to gravity is given. So the question could be, so first let me say what is given to us. So delta x, remember the 6 variables we have to look for: the initial, the final, and acceleration due to gravity. Always in kinematics. So of course this will be typically is written in a story. So someone is standing and throwing a ball up in the air, but your goal is to find out what how many quantities out of this is given to us. And since the stone is falling under gravity, immediately you know it's 9.8. Now, when we write 9.8, these equations are sensitive to positive and negative sign, right? It's a motion in one dimension. So direction, the only direction inbuilt in this is that whether it is positive or negative. So I have to be very careful about that. And it is very less error prone if you stick to always having the positive direction going up. Often it is convenient and easier to actually choose it negative, but you have to be smart about that. So if you know what you're doing, there is nothing wrong in choosing the axis in the going positive downwards. Often it is easier, but it is, if you don't know what you're doing, it is more error prone. So I will try to be consistent and do most of the examples with positive axis going upward. And unless I mention it, it will be implicit in there. So in that case, acceleration is minus. Right? And it's important that that's minus. Often, sometimes it leads to reasonable. That's one of the most common mistakes that happens. Once you have got the point, then the sign is the bigger mistake. Okay. So that's given to us, but we are looking for 3 quantities. So V initial is given to us 5 meters per second. So that's again plus. So it's plus 5 meters per second. V final, we don't know. We are not actually given to us, that's a future point. It's usually harder to measure. Also, this is easier to control, right? Initial velocity. Time, also, we don't know how much time it takes to reach the ground, but we are told how much distance it or what is the displacement. Notice this is the height, 20 meters. So even though the distance it goes is it might go up and come down. That's not 20 meters. It goes a certain height up and comes down. But the problem, our equation of motion understands that implicitly, and that is where the positive sign matters. Is it going that way or this way? That matters as to whether the equations will count that extra curve or not. But the equations are smart enough to understand that it is only the final minus initial, only the final and initial points matter. Pretty remarkable that the details don't come into picture. So final minus initial, this is a smaller number. If now at this point I've already chosen that to be positive, I can choose this to be 0. Not really necessary because it is a difference in the position. So whether even if I don't choose this to be 0, it's okay. But if you want, you can say this is x is equal to 0 here, and it is growing up. So if this is 0, that's 20 meters. So it is 0 minus 20. So that's minus 20 meters. Is this one. Even if I were to not choose 0 here, even if I were to choose 0 here, that would have been the same because this is positive. So this would have been minus 20 meters. So either way, I'll get delta x is equal to so much. So that's your 3 quantities. And now the question comes in. So I can either find out this or this. So let me say, what is a question? Let me find out how much time does it take to reach the ground? How much time does it take to reach the ground? Like right before it reaches the ground. So that's the so that means delta t. That's what we're looking for. That's the unknown if you want. And the quantity that we're not even discussing at all, that becomes a missing variable. And the way we motivated this whole exercise, even though this is not of interest in the problem, that plays an important role in our strategy, that decides which equation to use. Find the equation that does not have V final in it, and we learned that it is delta x is equal to V initial delta t plus half a delta t squared. That's it. So, and then we immediately plug in numbers. Right? Plug in the numbers. So that's minus 20. Let me drop the units. So just to avoid the clutter. That's positive. So it's plus 5.0 delta t. And that's plus half. And acceleration is minus 9.8. Again, dropping the units there. And delta t squared. That's a quadratic equation. Like we immediately see that, we recognize that, that's a quadratic equation. Put this all on one side to show that more clearly. This is a negative quantity coming to the left-hand side. 9.8 divided by 2 is 4.9. So that's 4.9 delta t squared. Bring it to the left-hand side. This, bringing it to the left-hand side becomes minus 5.0 delta t. And that's minus 20.0. It's crucial that you take care of these signs very carefully, which depends on your initial choice. Right? You have to be very careful with those signs because otherwise, remember, quadratic equation sometimes gives you complex solutions. If you don't choose the signs correctly, there is a chance that you might get meaningless solutions. So with that caution, let's solve this quadratic equation. We'll get 2 solutions, we know. But let's do this properly. Delta t, 2 solutions, minus b, right? So minus b is minus of minus 5.0, so it becomes plus 5.0, plus or minus square root of square of the coefficient linear coefficient of the linear term minus 4 times the coefficient of the quadratic term, so that's 4.9. And finally, the constant coefficient which has no time dependence, that's minus 20.0. That's in the square root, and this whole thing has to be divided by 2 times the coefficient of the quadratic term, so that's 4.9. Right, minus b plus or minus b square minus 4ac divided by 2 times a. That's equal to, inside the square root, notice this is where I was saying the sign, right? This sign has to cancel that. It is possible that if this was larger, then you can get a complex coefficient. And one should be careful about that. Sometimes it is possible that, yeah, there is no solution at all for this time, but most often we do have it, and then a wrong choice of sign will not give you that solution. So let's get this correctly. So square root of how do you do this? 4 into 4.9 into 20. So that's 320 and 25. So inside of the square root, I have 20, 25 minus 320. Sorry, not minus. Minus and a minus positive. So that's square root of 345. So it's square root of 345, and that's 18.6. So what we have is plus 5.0 plus or minus 18.6. It's only two significant digits because of the 9.8 there, and in the denominator we have 9.8. Clearly, that is a negative solution here because 18 is larger. So let me get the positive solution first. Yes, please.
Shouldn't 4 times 4.9 times 20 equal 392?
Oh, I did wrong, is it? Okay, hold on. Possible. 4 times 4.4 times 4.9 times 20. Hold on. That's 392. Yes, of course. Thank you. So this is 392. Thank you. I don't know what I was saying. Okay, 392 plus 25. So the square root changes, right? So square root of 392 plus 25. Thank you for checking on me. That helps. Okay.
Okay. Thank you too.
Yeah. Good. Good catch. So this is not 18.6. Bad. So that's 20.4. Okay. Hopefully that's correct. So going forward, so this is 20.4 plus 5 is 25.4 divided by 9.8. Right, so that's to two significant digits, that's 2.6 seconds. Well, very small time, right? If you throw a stone up, typically a second is 1001, 1002, 1003. That's how you look for seconds. And within 3 seconds, the stone has reached the ground, apparently, right? That's plus 2.6. That is one more solution. So it's interesting to ask, what is that solution actually? So let's look for that. That's 5 minus 20.4 and then divided by 9.8. Okay, so that's 1 minus 1.6 seconds. Clearly, if you're working on this problem, we know that time starts at t equal to 0, and it is going to reach the ground in the future, so in a positive time, right? So this is surely the answer, no doubt about it. This is the correct answer. This is, we have a mathematical equation that has two solutions. Usually mathematics means something. So it is not that it is completely meaningless. It's a curiosity could be, what is this time anyway? Like, does it have any meaning at all? So let's go back and look at this diagram again. So this is a negative time notice. What does that mean? So let's go back to this figure. So notice that as far as mathematics goes, it doesn't know that you have actually truncated your equation starting from initial point to final point. The mathematical equation doesn't know that there is a ground here, there is a roof there. Our mathematics equation tells us that this will keep going in the forward direction, and actually this will keep going in the backward direction also. So this all the way to minus infinity to plus infinity as far as time goes. And if you were to ask, where does the ball reach the ground? Yes, it reaches in the forward time. So that's plus 2 seconds. But there is also a negative time in the sense if you had imagined the ball to be coming from somewhere in the past, then it would cross this ground at this point, and it would take this much time to reach the roof, right? So in backward in time, it has actually crossed the roof, hypothetically, using these equations at minus 1.6. That's your minus 1.6 seconds. So it has meaning there. And this is equal to plus 2.6 seconds. In fact, this time has more meaning than that, in the sense there is so much symmetry in this problem. You could ask, what if I were to throw this ball downward with exactly the same velocity 5.0? Again, one can do the calculation. I won't do that here. But if you were to do that calculation, it would be exactly minus 1.6 seconds, because now you're going down, right? So that means to say that when it is going up and then when it comes down, right at this point, it will have exactly 5.0 meters per second. Again, not very obvious. Why should that be the case? You have to verify that. When you practice, you should check what will be the velocity right at this point. So again, you do what is delta x in that case? That's 0, right? Delta x is equal to 0 plus 5 meters per second and minus 9.8. And you ask, what is V final now, right? That could be an exercise you do, and it will come out to be exactly 5.0 meters per second by going downward. So there's a lot of symmetry in this problem, and that minus 1.6 seconds has two meanings. Like, one is that it is the past it crossed that ground, or it also is that if you were to throw the ball downward, that is the time in which it would reach the ground. So that's some understanding of that of this problem. So the way we have treated this problem, 5 variables, look for 3, find the missing variable, done. So it's pretty much a prescription. It seems like all the problem is just a matter of bookkeeping from that point on, right? Once you get the strategy, it is more of a bookkeeping. But that's not really the case, because it's not typically just one problem you do. Sometimes you can club these two problems, and then one has to be clever. So then there is a coupling that goes on. So let me talk about a problem of that kind. So let me move the camera to so where this prescription doesn't work. So basically, we can compound this. So instead of talking about one object falling, I can compound this problem as 2 masses. So that's a simple example that comes in. Later on, we will see projectile motion, where we throw a sort of in air, we keep an angle. Again, there will be a coupling there. So another simple way of coupling, again, this is an example in your homework also. Yeah, so we have about 15 minutes, right? I think I can attend to this problem. So let's say, so this is again an example. Right? It's also in your homework. Like, the numbers might be different because I don't remember the number in your homework, even though I made the solution yesterday. Okay, so what we are saying is there is a bridge. Bridge is, let's say, coming out of the boat. So this is a bridge, and that's the fence of the bridge, right? Think of this as a road, and you could walk. So the bridge itself is going into the boat. And that's a surface of water. So think of it as flat. So that's water. And there is a boat in the water. So that's boat. And the boat itself is moving with velocity VB. So I have to clarify what is happening. There are two things going to be involved. One is a boat, and that will be uniform velocity. So now that we have attended to one problem, which seems like it is just a matter of strategy there. So now we want to club two things, compounding the problem, right? So there are two quantities. One is a boat, which is having uniform velocity. Remember, uniform velocity is very simple. There are in 5 equations. There is only one equation. Distance is equal to velocity times time. That's only one equation when you're going with uniform velocity. And the second is, someone is going to drop, so one is standing on this bridge and they drop something from the edge of the bridge. So drop means you just leave it out there without any initial velocity. Let's say, I think in your homework problem, that's a key. A key is dropped, and once it is dropped, it actually falls with uniform acceleration, which is the acceleration due to gravity. Right? That falls straight down, so that's uniform acceleration. And uniform acceleration means 5 equations, right? 5 variables here, and there are 3 variables in there. But usually, time is the same for both. Right? That's the coupling. That's the connection between the 2 independent motion that is happening. Boat is independently going horizontally. The key is falling independently vertically, but the time is the same. Right? That's usually the coupling involved. And now let's frame the problem. We say that the key is dropped exactly when the boat is about a certain distance xb, right? That's the distance of the boat, horizontal distance of the boat. So by that time the boat has traveled this much distance, the key has traveled the vertical distance, so that when the boat really reaches here, the key just reaches the first, the initial or the left end of the boat. So that's the point. So that's a problem that we are designing. So let's say this is the distance delta y. Right? That's the key. Like if you want delta y k, that's the amount of distance that the key has formed. When it comes to the boat, there's only one equation. Delta xb is equal to velocity of b times delta t. Right? 3 variables here, but time is the same for the key also. So we next go to key. So that's your boat. And coming to the key, there are 5 variables. So that is delta x for the key, delta y, I said, right? So delta y for the key, because it's in the vertical direction, but it's the same equations that work. And that is delta, let's say delta t, and that is acceleration, which is minus 9.8 meters per second squared. Delta t, we don't know. Let's say delta yk. Let's give that some numbers in here. So this is let's I think it is 10 meters, if I remember right, from your homework problem. And the bridge, this could be about 25 meters, right? That's a possibility. Let's say that's 25 meters. So delta y is minus 25 meters. Remember, it is falling down. So again, a choice. We are keeping everything positive in the upward direction. Delta t is the connection between the 2 problems. But there are 5 variables to begin with. What is v initial? We are dropping it from the edge of the bridge. Dropping means we are just releasing it. So it's 0 meters per second. And v final, usually it is not easy to measure the velocity in a future time, right? So we don't know this. So notice we have 3 quantities immediately given. That means we can solve for these 2 using the vertical equations of motion. Once we know the time here for the key, the time taken for the key to drop from here, if we could measure the distance, how far the boat was right when it was getting dropped, then we have one information in here. And even though there are 3 equations, the time actually is common. These 2 are connected. That's the coupling between the 2 problems. So that's the trick. Usually there are 2 independent problems, but time couples them. So one problem can be solved, even though we are not asking for the time, solve for it, go to the next one. Once you know time, since you know delta x, we can find out p. So the question could be, so the question is, find the velocity, or find the speed or velocity of the boat. And naively, if I had not given you this strategy, you would say, oh, velocity of the board is given by the distance it travels by time. Oh, I don't know time, but the time is actually given through the information of the key falling down. So let's work on this problem. We want to find time, right? Why do I want to find time? Even though there are two quantities given, it's not asked about time at all because we want to connect it with the board. So that's your unknown quantity temporarily, and this is your missing variable. If V final is missing, it turns out again we have that same equation, right? We have delta x, no, delta yk is equal to V initial delta t plus half a delta t squared. And we would think that, oh, again, we will get a quadratic equation. Oh, I'm almost at the edge here. So we would expect that again we should get a quadratic equation, but it's a much simpler quadratic equation because V initial is 0. Delta y is minus 25. That's 0. And that's plus half. A is minus 9.8. And that's delta t squared. Notice the negative signs are important. Both sides, they cancel out. And I get delta t squared, which should be having a square root, right? So 25 into 2 divided by 9.8. And then you take the square root. It's 50 divided by 9.8. That's approximately 50 divided by 10. So that's 5 square root of 5. So that should be about 2 point something. So let me calculate that. So that's 50 divided by 9.8. And that's 2.56 seconds. Again, we need only 2 digits because 9.8 has only 2 significant digits. But I keep the third digit just so that the error doesn't propagate into the next calculation. And this is seconds, that's not 5. So that's units of seconds. Yes, again, I made a mistake.
When I plug it into the calculator, I get 2.26.
Oh, yeah, I do see 2.26. I think I'm writing the next digits. Yeah, thank you for correcting me like this. Yeah.
Thank you as well.
Yeah, no, thank you. I'm looking at it and I think I'm not reading it correctly. Bad, very bad. Okay, 2.26. I should read the calculator correctly. Yeah, thank you. So that's seconds, okay? Yeah. Please correct me. Yeah, thank you very much. That's necessary. Otherwise, it is very confusing when you go back home and it doesn't match. Okay, so now we have time, right? Once we have time, put this in the board equation. Board equation is very easy, right? Because it's you going with uniform velocity. It could have been accelerating. Then you have 5 more equations, 5 more variables here. It's a little more complicated. I try to fix or confine myself to one uniform velocity and one uniform acceleration. Coupling those two is what I typically do just to make it simpler. This is sufficiently coupled anyway. Okay, so what's our velocity of the boat? Our speed of the boat is, if I were to rewrite that, that's the displacement over time. How far does a boat go in the same amount of time? But that's now easy. So that's 10 meters. It's going to the left, but everything, let's measure it to be positive in the left. Otherwise, we have to say this is minus 10 divided by plus time. So it will be velocity will be negative. So it is going in the negative direction. That's also correct. Let's do that. So this is minus 10 meters, let's say, and divided by 2.26 seconds. Time is positive. So the velocity would be approximately 4, right? So it's 10 divided by 2.26. Right? That's 4.4. So that's equal to minus 4.4 meters per second. The minus sign means that it is going to the left. So here's a simple example where we were having 2 unknowns in this equation. There's only one equation consisting of 3 variables. Out of the 2 were not known. but we calculated one of the variables from another independent problem where the time was common between the two. So that's the, I've done only 2 examples, but notice you should go through the homework problems. I try to go through them in detail with a lot of explanation. So that also serves as an illustration. So it also helps you with your homework also for sure. But I think that could be a learning exercise too. But do extra problems. Try to do things on your own also. And I'll stop with that. I don't cross time today, so right at 50. So thank you and good luck.
Have a good night, Professor.
You too. Thank you, Blake. Thanks
You're
for
welcome.
finding the mistakes.
Bye.
You're
Thank
welcome. Thank you too.
Enjoy.